In this video, we're going to be looking at the distribution of chemicals, and we're going to review some of the heuristics needed to start building your first process flow diagram. Initially, when you're working with a new concept, you need to understand the market, the competitors, the prices, and uses of the desired product, and sometimes about the byproducts. You also do some benchmarking, and with that benchmarking, you start creating your preliminary data table. The reason is, right, if you go to this image on the right, is that the concept design requires you to understand the prior state of the art, or benchmarking what is out there that can mimic, right, the reaction that you want to complete, or what other type of reaction pathways are available for you to use. It could be things that are state of the art, like things in journals or articles, or it could be things that are in patents, old patents, or new patents. But you need to know what is out there in terms of functionality, in terms of uses, in terms of safety, and different other constraints that will depend on the scope of work, right, or the problem statement for your project. Connected to that is understanding the stakeholder constraints and criteria, and those stakeholder constraints and criteria become the way for you to narrow down to the best alternatives on your research. You then look at the materials or the raw materials, the physical state, the safety, and the manufacturing process that you can use potentially in your design. Then as you progress in your design, you start doing some preliminary economics, some business and marketing studies, and understanding the environment, including some initial cost, okay? And cost can be cost of raw materials, right, in the early stages. And as you progress, it could be the cost of utilities, the cost of equipment, and so forth. Then all of that should be complying regulatory environment. This could be a regulatory environment in terms of safety, or environment on human health, or aquatic, or environmental. This is important because as you refine and you create your concept, you're going to be optimizing all of this using these different constraints and different areas, right, on the concept design. And then finally, or initially, right, everything is embedded between all of these business aspects and designing aspects, but always taking the chemistry and chemical engineering fundamentals as a stepping stone for your decision process. This means that you cannot violate, right, any law of thermodynamics. You cannot come up with things that cannot be created, right? So you really need to understand your chemi fundamentals. So as I mentioned before, we're working on example with the vinyl chloride monomer. Here, when you do research initially, right, you're doing benchmarking, you come up with multiple reaction pathways. In my class, I recommend to have around 10 reaction pathways. And the idea is that you see what is out there. Sometimes you neglect some of the reaction pathways, but sometimes by reading the separations, or maybe seeing how they handle side reactions or byproducts, you may come up with new ideas in the meantime. So this is the example, right, with this vinyl chloride, and I have 5 reactions. And from those 5 reactions, I went through a process of selecting which one is the best, right? We went through a screening table and a scoring table. From there, we analyzed the results, and we found out that reaction pathway 3 and reaction pathway 1 may be the top candidates. And we like to have two candidates just because when you go to the simulator, sometimes you realize that you cannot simulate one over the other. But either way, of the two you pick, you know that it is the best option based on the different criteria that you selected in your concept selection process. So when you find out the winner reaction from your scope of work or for your particular process, you need to go back again to the literature and make sure that you have enough information to be able to simulate it, so you can have the best chemical reaction and the most profitable chemical reaction. But if we cannot simulate it with the tools that we have, it may be a problem, right, to understand the scale up, particularly in a project that has time frame, like the ones that we do in my class, right? We do a process design. We have around 15 weeks to complete the project. So we have to make sure that we can simulate it using the tools that we have available. Remember, always have information about the capacity, information about the specific reactions. If you have 2 reactions, 2 different steps in the reaction, that means that you're going to have 2 distinct reactors. In one reactor, you can have side reactions, so that will happen in the same reactor. So you need to understand, right, the conversion, the selectivity, and all that for your particular reaction. Then you need to have information that you can get in the literature. Maybe you have information about which components is in excess. You may have information about the residence time, or the volume of the reactor. Either of that information is important, especially when you do sizing later. Then you kind of summarize the designer comments just to remind yourself of the important aspects of this chemical reaction. So when you start building, before you start simulating, the first thing that you do is to create a preliminary block flow diagram. This is a very holistic overview of what the design will look. I like to do this in a piece of paper or maybe on a presentation slide. And the idea is that you can envision where is your goal, right? So you need to identify the raw material sources and physical states. The raw materials, they must come into the system as we find them in nature. If you need to process them and pre-treat them before adding them to the first reactor, that's perfectly fine. But it should mimic, right, what is out there and how we're gonna get the source of that raw material. So that is an important design parameter. You can also have, besides rock, like the actual chemicals, let's say chlorine or ethylene or whatever chemical you have here, you also need to consider other sources, right? You may have, instead of purchasing pure nitrogen or oxygen, maybe you want to use air, right? It's readily available, so you just need to add a separation unit, probably cryogenic, to separate the nitrogen from the oxygen. But I mean, air is cheaper than purchasing the nitrogen and the oxygen. You also have to consider, you can also consider syngas, right? That is synthetic gas or natural gas. All of them have different compositions of maybe reactants or building blocks, right? That you can use. Smaller molecules, right, are considered to be like building blocks, and you can find them in different ways. Then the second is back again, organizing, having clarity in terms of the information for your reactor, main reactions, side reactions, kinetic information, etc. Anything information in terms of the excess, if they're added in stoichiometric amounts, so forth. And then you organize the information for your products. You need to know the final physical state, right? You're not gonna sell a hot HCl gas, right? You need to make sure that the way that you're gonna be selling this is gonna be the way that is coming out from your process flow diagram. Once again, final physical states, the purity, the amount needed, particularly of the desired product. Convert any byproduct to more products if you can, right? The target is to produce the desired products. If you have a byproduct, try to find ways, instead of dispose it, to actually convert it into more product, because that's the target of your project. And if you can, sell all products or byproducts if you cannot mitigate them or treat them. The operating factor is one of the factors that has a major effect on the profits, and it's basically the fraction of time a process is in operation. Anytime that a plant is not producing a product, it is also not producing revenue. Downtime in production is separated into two different categories: planned and unplanned. When you're dealing with planned downtime, these are typically scheduled and budgeted stops during the production, such as scheduled maintenance and product changeover. So let's say that you need to maintain turbines because you're producing energy out of steam. So you can schedule that maybe twice a year, right? Every 6 months. You can also change products in line. Let's say that you're in a pharmaceutical company and you're producing 2 different drugs. And every 6 months, you rotate between one and the other, right? Or you have a schedule every 2 weeks, or depending on the type of product. But product changeover is really common in all industries, so it has to be added into the calendar and planned. Also, there could be unplanned downtime productions, and these are undesired. They occur when equipment that is scheduled to be in operation has an unexpected event, such as an equipment failure or running out of materials. You can have also machine jams, part failures, water and oil leaks, inadequate maintenance. Let's say that you scheduled something to maintain, but then something happened that didn't go well. Following the Van Burn research study, the reference is here, you can find that around 88% of companies have experienced at least one unplanned downtime outage over the past 3 years. The average numbers of outage are 2. Based on an independent research, they found that downtime ended up costing companies around $250K per hour. This equates to more than 2 million. So this unplanned downtime is important, right? This translates into economical losses. 70% of companies lack complete awareness of when equipment assets are due to maintenance or upgrades. So Having a system in place can actually save some money at the end. Zero unplanned downtime is now the number one priority or highest priority, right, of around 72% of the organizations interviewed in this study. Remember, field service management is directly tackling the problem of unplanned downtime with basically with latest digital capabilities, shifting service maintenance and downtime from reactive to predictive. So a lot of things here in terms of process control, artificial intelligence, trying to understand the data of production to be able to predict, right, when this downtime happens and be proactive instead of reactive. There are multiple costs associated to downtime. The first one is, of course, the loss of production. The loss of production has an impact on the sales. Loss of capacity, right, the total amount of capacity that the plant can target. If your process is designed to produce a certain amount of product and now you are producing less because you have some equipments down, that means that it will impact the sales too. Also, it can impact the direct labor. Direct labor can be more costly because if you have a personnel in the plant, but you're not selling anything, that means that the cost per labor will be increased as compared to the amount of sales or profit of the company. And also the cost of storing the inventory, right? If you have the raw materials because you're not using it because the capacity is down, you have to pay for that. Anything in the inventory means that it's not being sold. So if it's not sold, that means that there's no money coming in and there's no profit. So it is important, right, the operating cost and taking that into consideration so we design our plan correctly. When we are creating a process flow sheet, first we determine the scale of the process and the production rate capacity. We know, for example, for this particular statement that the operating factor is around 0.90, right? It's the 0.90 of the total days of the year is when the plant is in operation. You can multiply the capacity of the plant, the target capacity of the plant for the product, and that will tell you how much the downsizing right on capacity will be due to the plant's scheduled downtime. This translates right into 101 and 500 pounds per hour. And we transfer that into pounds per hour because usually these are the most common units used in simulators. However, simulators can convert units from one and the other. I'm more used to use pounds per hours or kilograms per hour if you're changing units to the SI system. The thing is that all of this number translate into cost, losses, right? We know that because we need to plan, instead of producing the target amount, now we're producing less because we have to plan for that. That means that we're losing around $32 million per year, right? Or things that we could have sold, right? If we have the 365 days of work of the year. So it is important to consider, right, the process flow sheet. In the process flow sheet, the operating factor, this will impact the scale of the process, the size of the equipment, the amount of utilities, the amount of raw materials, everything in the economics, right, will be affected by the scale. For this initial part of this video, right, basically at the end of the day, what you want to make sure is that when you add your reaction scheme, you have all the information to input that into the reactor. It could be a conversion reactor, a kinetic reactor, equilibrium reactor. Then you can not only talk about the type of reaction, but also talk about the type of reactor. It could be flow reactor, a CSTR. It could be a packed bed reactor. There are different type of reactors that you can pick. And there's also a couple of functionalities, like in HYSYS, we have things that are called the adjust and set, and those adjust and set allow us to specify feed composition based on the target, which is our product. So there's video available in my class regarding that particular topic. Also, adding tables to the process flow sheet allow us to quickly see changes that we're tracking in a particular part of the process, besides downloading the workbook or the final tables, right, for the whole process.